Hey there, and welcome. When you look at a huge industrial plant like an oil refinery or a power station, have you ever stopped to think about how it all stays in perfect balance? It's not magic, right? It's a very precise science, the science of control. And today, we're going to pull back the curtain on how engineers pick just the right strategy to keep these massive, complex systems humming along without a hitch. So, let's just jump right into the big question. How in the world do you control what seems like total chaos? You've got a system with literally thousands of moving parts, all these different variables like temperature, pressure, flow rates, everything changing all at once. Keeping that stable, that is a huge, huge challenge. And the answer, really, it all comes down to choosing the right control strategy. All right, so here's what we've got on tap. We'll start with the basic idea, this constant balancing act. Then we'll get into the two main ways of thinking, reactive versus proactive control. After that, we'll go through a really practical 5-step guide for picking your strategy, and we'll even look at a tricky situation where one controller just isn't enough. And finally, we'll wrap it all up. Sound good? Let's go. Okay, Section 1, the constant balancing act. Let's really set the stage here. What is the fundamental problem that every single industrial control system is trying to solve? Well, you can boil it down to one simple idea: fighting disturbances. See, here's the reality of it. No industrial process is ever just sitting still. It's always in motion. The stuff you're putting in, the raw materials, they change. Equipment gets old and wears down. The demand for whatever you're making goes up and down. These are all what we call disturbances. And the whole job of the control system is to fight them off and keep that one critical thing, whether it's temperature, pressure, you name it, locked in right where you want it, no matter what gets thrown at it. All right, on to our next section, reactive versus proactive control. So if we know we have to fight these disturbances, the question is, how? And really, there are two main ways to think about it. You can either wait for things to go wrong and then react to fix it, or you can try to see the problem coming and stop it before it even starts. That's really the core difference between these two philosophies. Okay, this is where the driving analogy really works perfectly. Think about feedback control as being reactive. You're driving along, maybe you get distracted for a second and you notice, oops, your car is drifting over the line, so you correct the wheel. You reacted after the error happened. Now, feed-forward control is proactive. You're driving and you see a big curve coming up ahead. You don't wait to drift, you start turning the wheel before you even get to the curve because you're anticipating what needs to happen. That's the key difference right there.
Now, there's a good reason why feedback control is the absolute workhorse of the industry. It's super robust. It doesn't need to know every single tiny detail about how your process works. And best of all, it will eventually correct for any disturbance, even ones you didn't know existed. But, and this is a big but, its greatest strength is also its greatest weakness. An error has to happen first before it does anything. So perfect control? It's just not possible. It's forever playing catch-up.
Feed-forward control, on the other hand, well, this is the psychic. It's the visionary. In theory, it can achieve perfect control because it acts before the process gets upset. But like a psychic, it has a huge blind spot. It can only deal with disturbances that it can actually see and measure. If some other problem pops up that it wasn't designed to look for, it's completely blind and helpless. Plus, to make it work, you need a really, really accurate model of your process, and let me tell you, that is not always easy to get.
Okay, let's make this real with a classic example, a boiler drum. You've got to keep that water level just right. Now imagine another part of the plant suddenly needs a ton of steam. Whoosh! It pulls it right out of that drum, and the water level starts to drop. A standard feedback controller would see the level dropping and go, oh, we need more water, and then open the valve. It's reacting. But a smart feed-forward system? It measures the steam as it's leaving and immediately says, hey, we're losing this much steam, so we need to add exactly this much water right now. It adds the water preemptively, and the level barely even wiggles. See the difference? So you might be thinking you have to pick one or the other, right? But here's the secret. In the real world, you almost never do. The best, most robust systems use them as a team. You use feed-forward to do the heavy lifting. It handles all the big, known disturbances you can predict. Then the feedback controller comes in behind it to provide what we call trim. It's like a fine-tuning step, cleaning up any little errors that the feed-forward system might have missed. It's really the best of both worlds.
Okay, so we've got the building blocks down, but how do you actually pick the right tool for the job? For any specific problem, how do you decide what to do? Well, thankfully, it's not just guesswork. There's a real method to the madness, a logical process you can follow every time.
And here it is, a clear 5-step framework. First, you've got to know what you're trying to do. Identify the control problem. Step 2, you have to understand the system you're working with. Analyze the process model. Then, based on that, you pick your weapon. Select the control algorithm. Step 4 is crucial. That's where you dial it in by tuning the parameters. And finally, you make it happen. You implement the code. It's a perfect little roadmap from what's the problem to okay, it's solved.
All right, let's get into the weeds with a really interesting challenge. We're going to take that 5-step process and apply it to a situation that's, well, it's pretty tricky. It's a common strategy that looks super clever at first glance, but if you don't look closely, you'll miss a really big problem hiding just under the surface.
This is something called split-range control. The idea is actually pretty simple. You can think of it as one brain, multiple arms. You've got just one single controller, but its output signal gets split up to control 2 or even more different valves.
So check this out. Here's a great example, controlling pressure in a separator. When the controller output is between 0 and 50%, it's only opening valve A, which goes to the flare stack. This is your emergency get rid of pressure fast valve. Then, once you get above 50%, valve A is already wide open, and now valve B, which goes to a compressor, starts to open. This is for your normal day-to-day pressure control. On paper, it looks really efficient, doesn't it?
I mean, it seems like a really slick way to make one controller do the work of 2. But let's go back to our 5-step guide. Remember step 2? Analyze the process model. Because when you really analyze what's going on here, a massive flaw starts to appear. Any ideas what it might be?
And boom, here it is, the tuning dilemma. Think about it. That flare valve, for emergencies, it needs to snap open super fast, but the compressor valve, it needs to move nice and slow and steady so you don't mess up the compressor downstream. Here's the kicker. A single controller has only one set of tuning parameters. It's like it only has one personality. You can tune it to be aggressive and fast, or you can tune it to be calm and slow, but you can't tune it to be both at the same time. So if you tune it to be fast for the flare, you'll make the compressor unstable. But if you tune it to be slow for the compressor, the flare won't open in time during an emergency. You're completely stuck between a rock and a hard place.
So what's the real solution? Well, you have to abandon that clever-looking split-range idea. Instead, you give each valve its own dedicated controller. You install 2 of them. They both look at the same pressure, but one is completely dedicated to that flare valve, and you tune it to be super aggressive and fast. The other one is dedicated to the compressor valve, and you tune it to be gentle and slow. Now each controller is perfectly optimized for its own specific job. Problem solved.
So after walking through all that, what should you really walk away with? Let's boil it down to the key takeaways.
Okay, first things first. You've got to understand the fundamental trade-off between reacting to a problem and anticipating it. That's feedback versus feed-forward. Second, have a system. Don't just wing it. Use a methodical, step-by-step process to analyze your problem. Third, you got to be a bit of a detective. Always look for those hidden complexities, just like that tuning dilemma we found. And finally, remember this. The goal is always to get the best possible control, not just to use the fewest parts. Sometimes the right answer means using more hardware to get the job done right.
And that brings us to one last question to chew on. We've been talking this whole time about how engineers make these decisions, but as automation gets smarter, as AI and machine learning get woven into the fabric of these plants, are we heading towards a future where the perfect control strategy just chooses itself? A system that can analyze its own behavior in real time and automatically pick and tune the best approach all on its own? It's something to think about. Thanks for joining me today.